Hello and welcome to the demonstration video for the Smart GPA made by the team consisting of Nicholas Zolo, Daniela Otero, George Darden, and Jennifer Castillo. If you've already seen our presentation video, you should know a bit about how the system works already, so let's get right into the demo. The use case is basically for the distance sensor to track a car coming in or pulling out of the garage and get accurate distance measurements so that it can give the proper feedback to its user. However, there are a few complications. It should be able to work at any time of day, under any lighting conditions. It should be able to pick up the car early as it pulls into the garage, without letting it too close without getting a measurement. In addition, the system should avoid all false positive measurements. It is preferred that the system miss a measurement, rather than get one false positive measurement. To perform the demo of the use case, we set up the system so that the laser dot would be relatively stationary on the car as it pulled in and out of the garage. However, the conditions were not ideal for identifying the laser dot, as the sunlight was very bright outside. Despite this, we were still able to get some good results. As you can see, as the car pulls in towards the distance sensor, the number displayed on the operation mode GUI goes down, and the LED lights change their color to indicate for the user to stop. In this way, it's working as intended. In addition, when the user pulls out, you can see the opposite change happen as the measurement displayed on the operation mode increases and the LED lights change to indicate that the user is pulled away a decent distance from the wall. It is able to pick up a distance measurement of the car as it is pulling out at a fair distance, even despite the adverse lighting conditions. The first specification we'd like to demonstrate is the measurement accuracy of the Smart GPA's distance sensor. The specification for this was to be within 10 centimeters of the actual measurement at any range. However, we found early on that this was rather easy to achieve compared to our other specifications, and that's because it's very easy to tune the accuracy of our system by changing the angle between the laser diode and the camera, or by changing the internal angle within the code of the distance sensor. By doing this tuning process, we can often get our accuracy within 1 or 2 centimeters of the actual measurement. To demonstrate the accuracy of the Smart GPA distance sensor, we've placed a number of markers at set distances away from the system. Here we can see the measurement when placed at the 300 centimeter marker. Here we can see the measurement at the 200 centimeter marker. Here we can see the measurement at the 150 centimeter marker. Here we can see the measurement at the 100 centimeter marker. Finally, here we can see the measurement at the 50 centimeter marker. The next specification we'd like to demonstrate for the Smart GPA is its operating range, which is specified to be between 1 to 10 feet. The measurement range is determined by when the laser dot is visible, so it can depend on the lighting conditions in the area as well as the surface of the object the laser dot is shined upon. The close range of the Smart GPA will never be better than about 0.8 feet because any distance smaller than that will make the laser dot not appear on the camera's FOV. However, the maximum range can theoretically go out higher and higher, even beyond our specification, However, the surface must be very optimal for the maximum range to go far beyond 10 feet. To demonstrate the measurement range of the Smart GPA, we got a free space of about 14 feet in which to move an object in front of the distance sensor. Here you can see that even at the range of 14 feet, the distance sensor is still picking up measurements. We then move the object to the specified maximum range of 10 feet and it picks up measurements there. We then move the object to the specified close range of 1 foot and it is picking up measurements there. However, you can see that if we move the object any closer than 1 foot, it stops picking up measurements at about 0.8 feet. The next specification we're going to demo is the measurement rate of the Smart GPA's distance sensor. It was originally specified to be at least 20 measurements per second, but it has since been lowered to be 8 measurements per second instead, due to the performance issues of our hardware. Due to the multi-threading approach we use for image processing, the measurement rate of our distance sensor is equal to the rate of image acquisition by our camera. Therefore, to test the measurement rate of our distance sensor, we must test the FPS of our camera, and we wrote a special script to do so that will print the FPS of our camera after taking 100 frames to the GUI display. Since the FPS test is not implemented into the GUI yet, we have to run it from an external terminal, as shown. However, when it's done running, its output will be printed onto the GUI, as you will see here, and as you can see, the frame rate is 10.3, which is greater than 8, and thus fulfills our specification.
In this section of the demo, we will go over the graphical user interface, specifically idle mode that's responsible for customizations and settings. So here we can do account creation and management, and general settings like changing light colors, maximum and minimum distance bounds, and the overall look and feel of the GUI. Let's begin. We will first demonstrate the login feature. So here we have a username of student and a password of password. It doesn't exist yet, so we will first sign up and then click login. We'll see that we received a notification. Okay, we're in. So now we can go to our account settings. First, let's demonstrate updating the username. So the old username is student, and let's say the new one, we will change it to student1, and we will click update. Now let's do the same thing for the password. The old password is simply password. Let's change it to testing, and we'll click update. And for now, we'll disable any account settings. This has the same effect as logging in. Now we'll go over the general settings of the GUI. First, let's start with set color scheme, and that takes place right away. We will choose between 2 colors, and that will serve as a gradient for the overall look and feel of the GUI. As you can see, we can choose between 2 colors and it will smoothly transition between. Now let's set the minimum and maximum distance. This means that this is the minimum and maximum bounds that will be recognized by the distance sensor. And now we can change the light colors, and this effect takes place after we restart the distance sensor. So if we choose the first color, that means stop, the second color means slow down, and the third color means keep going. Now let's save the settings and we can exit out. For full transparency, we'll now demonstrate changing the light colors. Take note of the colors that I choose. And one of our members will demonstrate now how it works. Take note of the changing light color immediately. In this next clip, we will demonstrate changing from idle mode to operation mode. This will happen very quickly, as you can see here. As soon as a laser beam is detected on the image, idle mode switches to operation mode. Right now, since we set the maximum bounds to 100, you will see that it will not go beyond this value, even though the distance sensor is currently calculating over 100 centimeters. Now let's demonstrate changing units. Take note that we are in feet, and immediately operation mode is fired whenever the distance is detected. Now one of our members is going up to about 4.5 feet. This would be a good time to mention that after 10 seconds of no input being received, operation mode will go back to idle, but that's not happening here because the distance sensor is currently in use. Now let's show her in action.
One of our specifications was that our input voltage be less than 12 volts, so that our device could be considered a low voltage smart home device. All of our components met this requirement except our display. After some trial and error and deliberation, we decided to use a larger display for our demonstration videos. This display does not meet this requirement as the input voltage of larger LCD displays is usually around 120 volts. Yet this display was used primarily to demonstrate and highlight our other features for our final demonstration. Besides the display, all of our components were powered using an input voltage of at maximum 5 volts. Nearly all of our components were powered using a 5-volt universal power supply during the final demonstration except for the display.
With that, that's the end of our demo. Thank you very much for watching and have a nice day.